Lesson 3, some constants used in nuclear and particle physics. Now, in the last lesson, I talked about the basics of nuclear physics, and one of the things I talked about was certain units that are used in nuclear physics. Now, we are going to see some constants that are used in nuclear and particle physics. Not like they are some new constants, they are constants that you have seen them, but we are going to see how they are expressed using the units that we talked about in the last lesson. We are going to look at the speed of light, Planck constant, and then we'll do a little exercise, and then we'll talk about the reduced Planck constant, which is just Planck constant divided by 2 pi, which is also called h bar. And then we'll do another exercise, and then talk about h bar c, which is a constant that is used in so many calculations. And then we'll also talk about the fine structure constant. And finally, we are going to talk about the constant e squared divided by 4 pi epsilon naught. So let's go ahead and see how these quantities are expressed using the units that we talked about in our last lesson. So we are going to start with speed of light, and from Wolfram alpha, speed of light c is 2.998 times 10 to the 8 meters per second. Now, the quantity contains meter, and meter is not a common unit in nuclear physics. Femtometer is more common, and and we know that femtometer is 10 to the minus 15 meter, or meter is 10 to the 15 femtometer. So, in the place of meter in C equals to 2.998 times 10 to the 8 meter per second, we can substitute for meter, and we are going to have 2.998 times 10 to the 23 femtometer per second. So don't be surprised to see this as the expression for speed of light that you are going to use in calculations in nuclear physics. Planck's constant. The symbol for Planck constant is H, and to four significant figures, Planck constant is 6.626 times 10 to the minus 34 joules second. Again, it contains joule, and in nuclear physics, we mostly use electron volt or any of its derivatives like kilo electron volt, mega electron volt, giga electron volt. And we know that 1 electron volt is 1.602 times 10 to the minus 19 joule. If you don't know how this came about, you can consult lesson 2, where I actually talked about the derivation of these units. Or we can say that joule is 1 divided by 1.602 times 10 to the minus 19 electron volt. So if we substitute in the place of joule this value, we are going to have 4.14 times 10 to the minus 15 electron volts second. So this gives us the relationship of Planck constant, or the expression of Planck constant in terms of electron volt second. We can equally express it in mega electron volt second, kilo electron volt second, and so on, by using the relationship between electron volt and the derivatives. Let's take, for example, mega electron volt. We know that electron volt is 10 to the minus 6 mega electron volt. So in the place of electron volt in what we have just derived, we can substitute 10 to the minus 6 electron volt, mega electron volt, and we are going to have 4.14 times 10 to the minus 21 mega electron volt seconds. So in the next exercise, I want to see how you can get the expression for Planck constant in terms of kilo electron volt second and giga electron volt second. The reduced Planck constant, which it is normally called h bar, is primarily used in quantum mechanics to simplify equations related to angular momentum and quantization, particularly when dealing with atomic and subatomic systems. Now, this makes it very relevant in nuclear physics because nuclear physics is a subatomic system. And it is essentially the Planck constant value divided by 2 pi. So I've expressed it in 3 units, in the standard SI unit, in electron volt second, and in mega electron volt second. So the next exercise is to see how you can express it in terms of kilo electron volt second and giga electron volt second. H bar C is used in nuclear physics to make calculations easy, and it is obtained particularly when H bar is in mega electron volt second and C is in femtometer per second. And if you multiply the two, it gives us approximately 197 mega electron volt femtometer. Now, the fine structure constant, which is denoted alpha, is a fundamental physical constant that measures the strength of the electromagnetic interaction between charged particles. Remember, we are dealing with nuclear and particle physics, and in particle physics, we have charged particles there. So it is very essential in our study of nuclear and particle physics. The fine structure constant alpha is essentially equal to E squared divided by 4 pi epsilon naught H bar C. And in that formula, we know what H bar C is. The other constants there are electronic charge, which is 1.602 times 10 to the minus 19 coulomb, is denoted as E. While we also have epsilon naught, which is the permittivity of free space, which is 8.854 times 10 to the minus 12 farad per meter. So we'll first of all start by simplifying that unit farad per meter to take the form of the units we desire to see in nuclear and particle physics. And when we do that, we end up with 1.602 times 10 to the minus 28 coulomb squared per mega electron volt femtometer. And we can now substitute that value into the expression for epsilon naught in the place of farad per meter. If we substitute that value, we end up with 1.418444089 times 10 to the minus 39 coulomb squared per mega electron volt femtometer. Now we have written all the digits so that at least we should get the results that we are looking forward to have. And if we now substitute the values of epsilon naught, the electronic charge E, and H bar C that we have already calculated, we end up with 0.00073 without any units. So it's a dimensionless constant. You can check it for yourself. All the units will cancel out. And if we can express it in terms of fraction, we simply have alpha as 1 divided by 137. And finally, this constant is essentially very simple. Is one of the constants we are going to come across as we study nuclear and particle physics. It is simply obtained by multiplying H bar C and the fine structure constant. And it has the same unit as H bar C. And the value will give us 1.44 mega electron volt femtometer. Okay, so we have come to the end of this lesson. Next lesson is going to be on mass defects and binding energy. If this lesson has been helpful, why not support me by your likes, shares, subscription, and click on the notification bell to be notified when the next video drop. Thank you. This is Physics with Omia.